Okay, so now we've looked at two gas laws. All right. First one was Boyle's law, and that rules pressure and volume. And the way to remember that is when you have a small balloon in the palm of your hand and you squeeze it, you put pressure on it. Okay? What happens to the volume? It's like my hamburger here. Imagine the hamburger. Actually, the hamburger is full of air. Okay? As I put more pressure on it, what happens to its volume? As you release the pressure, what happens to the volume? It goes up. That is Boyle's law. And it's P1 V1 equals P2 V2. That one you don't have to write anywhere on your periodic table because it's on the back of it in a chart labeled, curiously enough, gas laws. Okay? The second gas law that we looked at on Friday was Charles' law, and it governs hot air balloons. You want to go up on a hot air balloon, you increase the temperature of the air in the balloon. As that temperature increases, the volume of the balloon increases, and the balloon becomes less dense. So what gets it up into the air? The cool air around it will push it up. What happens if you want to come back down to Earth? Let it cool down. Cooling it down makes the volume of the balloon go down, which increases its density until it's dense enough to be brought down by what? Gravity. Yes.
So, whatever if the cold air is more dense than the not cold air, and how is it pushing up if it's continuously falling?
It's not. The air around it is flowing underneath it.
Oh, because
Right. And it flows underneath, and as it fills in the space underneath, it pushes it up. Remember the green water over the clear water? You know how the cold water was able to push the green water up?
yeah.
Okay, we have seen what effects temperature and pressure has on volume of a gas. And what about the effect that temperature has on the pressure of a gas? I think we got as far as seeing it on simulation, right? As temperature goes up, the pressure goes up, vice versa.
True story. During one of the coldest stretches of the winter, I started up my car and saw this warning light. That's right, the tire pressure light. An easy fix, unless it's a flat. So I jumped out of my car and was happy to find, in fact, it wasn't a flat. The tires just needed a little air. Thinking back to high school chemistry class, I decided this makes complete sense. Remember the equation, the ideal gas law, PV equals nRT, where P is pressure, V is volume, N and R are constants, and T is temperature? Well, the air in your tire is a gas, so it more or less adheres to this equation. Assuming the volume of your tire does not change, the ideal gas law basically says that as temperature changes, so changes the pressure. So imagine the air molecules in your tires as just a bunch of little tiny orbs. The tire pressure can be thought of then as how often these orbs collide with the walls of the tire. When it's warm, the molecules will move around all over the place, bouncing off the walls and each other constantly, and hence, pressure is higher. When it's cold, however, the molecules slow down, collide with the walls of the tire less, and so pressure drops. It's a good idea to keep your tire pressure a little higher in the winter then. Most tires suggest keeping the pressure at 32 psi. Keep in mind, you may have to let a little bit of that air out when warmer weather returns in the spring and summer months.
Okay, so it's wintertime and it's really, really cold outside. Talk to me about the molecules inside your tires. Are they moving fast or slow? Slow. As they're moving slow, they're not bouncing around much. And it's that bouncing that causes pressure. So that's why you could have an absolutely no flat tire, but because it's so cold outside, it looks kind of droopy. And if you were to measure its pressure, it's below pressure. On the contrary, maybe not here in East Tennessee, But people in southern parts of California and Arizona have to worry about this. They call Death Valley because that's where tires go to die. Actually, no, they used to call it Death Valley before they had automobiles. Okay, but a lot of tires do die on the road between Las Vegas and LA. A lot of tires die during the summer. Why? You inflate your tire, it's just perfect, spot on, 35 psi. You're going down the road and you blow a tire. Why? Well, temperatures outside during the summer months can very well get up to 115, 120 degrees Fahrenheit. And add that to the road temperature, add that to the friction that's already on those tires, and you could have the potential for a blowout simply because the pressure is too high. So that is why they're always warning you to monitor your tire pressure, especially when you're driving long distances on very, very hot roads. Which law describes this phenomenon? The Gay-Lussac's law. And it's similar to Charles' law, but instead of V, it's P. P1 over T1 equals P2 over T2. All right. In each of the three gas laws, there was always one factor that remained constant, while the other changed. Why is this an unrealistic expectation? Well, let's go through these again. Didn't really harp on it, but I want to harp on it now. Boyle's law was P1 V1 equals P2 V2, and I kept the temperature the same. I didn't allow the temperature to change. Charles' law was V1 over T1 equals V2 over T2. This time I did not allow what to change? Pressure. And then looking at P1 over T1 equals P2 over T2, I did not allow volume to change. Fact is, it's kind of hard to be able to stop that from happening. So it would really, really, really be nice if there was a law that factored them all in. And that is the combined law. P1 V1 over T1 equals P2 V2 over T2. And of course, this runs
Hey everybody, I'm Ben.
I'm Lauren. This
most-
is Brain Stuff.
This is beyond anything else the most important application of the combined law.
Oh, right, yeah.
And that's why we're here. Today's question is, how does popcorn work?
Yeah, it's weird. You take a pouch that's no bigger than a wallet, you put it in a microwave oven for like 3 minutes, and suddenly it's expanded to 40 or 50 times its original size? What?
It's pretty wild, but there are actually 3 really simple elements that make it work this way. So first there's moisture inside the kernel. Then you've got starch also inside the kernel. And then the kernel itself is a hard but not too hard shell that's completely surrounding everything else in there.
Oh, okay, so when a popcorn kernel heats up, either in a popcorn popper or in a microwave oven, that moisture inside the kernel turns into steam and it tries to expand.
Right, but it's prevented from doing so by that hard shell. Eventually, when the pressure builds up enough, it will explode.
Okay, well that part seems kind of normal. Like I don't want to be sketchy or anything, but a lot of things explode when you heat them. Right?
Not that we know anything about
Right.
that here.
Yeah. Okay, but be cool. The strange part is the white solid stuff that forms during this process. Yeah?
Well, it's not really that weird either. I mean, bread and muffins do that, albeit at a much slower pace, and technically that's a chemical reaction, not a physical one.
If you really want to see popcorn in action, there are 3 experiments you can perform to get a better understanding of these principles. Oh, I forgot the first one.
The first one, and it's really experiments of inaction. You can take a push pin or a needle and use that to puncture the shells of some popcorn kernels. Wear safety goggles when you do this.
Yeah.
It's harder than it looks. But yeah, so these things won't.
Ever wondered why there's always kernels down in the bottom of the container that are not popped? Remember, you've got to have that moisture inside the kernel. The kernel has to be tough enough to withstand a lot of pressure. So what happens is, as that water gets turned into steam, the pressure builds up. The pressure becomes so great that it actually liquefies the white stuff, liquefies it, turns it into a liquid. And then at that point, the shell can't take the pressure anymore, and it lets go, and the thing explodes. Of course, that liquid, as it comes pouring out, exploding out, solidifies within a second. And what you have is a popcorn. The ones that are dead down on the bottom, they probably have some kind of crack in them that allows the steam to come out. If the steam can't build up inside, then it can't liquefy the starch. And if you can't liquefy the starch, then you don't get that exploded.
Pop once they've been punctured because the pressure cannot build up inside the shells enough to do so.
Oh, and the second one, you can let new kernels stand in a warm oven or in the sun for a few hours and then try popping them, right?
Right, because that will dry them out.
Yep, and they won't pop nearly as well.
Yeah, no, I mean really low, ineffective rate of popping, really.
Minimum poptitude. Third, you can try to pop popcorn at a low temperature, like below 300 degrees Fahrenheit.
Oh, which is 149 Celsius.
Good call. It won't pop. The moisture inside the kernel will turn to steam at water's boiling point, which is
100 degrees Celsius, aka 212 degrees Fahrenheit.
You are crazy good at this. And it will liquefy the starch, but it has to get above 300 degrees for the pressure inside the kernel to build to that point where the shell explodes.
Right. Once it does so, the soft starch will burst out, and due to the relatively cool air outside of it, it will cool down really rapidly to form that unique popped kernel that we all know and love.
Which is like a snowflake that you can eat at the movies.
I love delicious snowflakes. That's great.
I mean,
And now you get to see the slow-mo guys. Okay, so the guy on the right, I want you to keep an eye on him because he's a perfect example of why I say that boys from age 15 to 25 are idiots. Okay? If that was a girl, when she starts getting splattered with hot oil, she would back away. But notice the guy in the blue.
Hello. Welcome to this slow motion video.
I feel like I'm on a cooking show.
Popcorn. So we've got some popcorn. It's the microwave stuff, I hope it works. Do you want to light that bad boy up? Actually?
Yeah. Isn't that hot looking?
Yeah, that's hot. So, yay! Do you like cooking shows?
Yeah, I love cooking shows.
First, add the popcorn.
I've always wanted to do this.
Have you?
Yeah.
You've never done it at home?
No. What? It's like half made.
Now we wait. Oh, they're going. They're going.
Oh,
Forgot
see
to
you
turn on the
later.
camera.
Flippin' heck. We'll wait for one to leave. There we go. That was good. So we're gonna go for. Let's put one on there.
Yeah, one.
Get like a buttery one.
Butcher one.
You have a battery thing for it.
Yes.
Oh!
The solidification of the liquid starch happens so fast that even the camera can't capture it.
Whoa! Whoa! Ah!
Get burnt here.
And wear gloves. Ah!
It hurts.
Yeah. What do you reckon? Ow! Ow! My face! Ow!
See the steam coming off of it?
Now that looked cool, but there was one down there that just sort of, even at 100 times slower, just went and went. I reckon we up the frame rate.
Yeah.
Ah! Alright, I'm going to man the camera because it's such a small frame now, but this is at 10,000 frames a second. Oh! Ah! Alright, we got it. Oh, whoa!
Watch this. This is cool. No, gotta go on. Gotta go on. What is STP? Standard temperature and pressure. Make sure you copy that down because you'll need it. 273 Kelvin and 1 atmosphere. Hold on a second. I think I may have